Okay, so this is a repeat of a recording I made yesterday. Today hopefully my voice is a bit better, but in particular I think I've switched back into an older microphone that I believe should not give me the same type of issues I had with the recording yesterday. So, what we are going to do now in the course is switch gear a little bit and move into looking at graphs or networks. And the reason why we look at networks in a graph in a course on math of data science will become sort of obvious as we move forward, but I'm going to give a brief introduction now, and then I'll move on to some mathematical properties of graphs, and then we'll see applications which will really tie this in with data science. So that's it. I'm going to start with, as I said, a very brief introduction on why it is that we use graph and networks in data scientific applications. And I'll start with a little sort of a disclaimer to make it clear that graph theory sometimes is a little annoying because the vocabulary is now almost good in the sense that it's unambiguous, but it took a long time to get there, and that means that books that are not so old might use some very different terminology. And this is something that you would see, for example, if you look at the older slides that I recorded in 2021, I believe, and other videos, and I mean in the slides that I use in these videos, because in there I was using an old book by a guy called Berge, who did a lot of things about graph theory in the early days, well, not early days, but in the 50s, 60s, etc. And the vocabulary, as I said, has evolved quite a lot now. Another disclaimer is that you probably know graphs as networks, and the two are usually essentially the same. In mathematics, we tend to think of networks as graphs with weights, but I'll use both terminologies sort of equally. I will mostly say graphs, but from time to time we'll talk about networks. So let's start with essentially what is the defining example of and the starting example of graph theory. So this is called Euler's Bridges of Königsberg. So that was it is a German city. I don't know if it still has that name, but it was a German city at the time. And the idea is that there are two islands in the center of Königsberg, and these two islands are linked to both sides of the mainland. So the river makes divides here, and the islands are connected to the mainland by a set of bridges. And Euler's problem was: is it possible to take a walk through this city and cross the 7 bridges that are there, cross each single bridge a single time, and never cross a single bridge twice? Okay, so can you take a walk from one place to another place, etc., go across all the bridges, but never cross the same bridge again? And we'll come back to that later. But what that led Euler to was to formulate the problem as what's called a graph that I've represented here. So the idea here is I've indicated as red dots what are called vertices, but in network theory you would call nodes, for example. So we'll use both terms. I'll typically stick to vertices. But sorry. I've indicated the vertices that are the different, if you want, neighborhoods, sides of the river, And I've indicated with these that we'll call edges the different bridges that exist between the different neighborhoods. Okay, so you can see, for example, oops, I need to make myself big again, that between this and this, there are two bridges, which we've indicated with these two edges. Okay, so this is a graph. And the question then is, well, we'll see later, but essentially the sort of mathematical way of formulating the question, and we'll see that this is not the definite way of writing it, but the question that we'll ask is it possible to find what's called a trail, okay, that's going along the graph, that contains all the edges, so all the bridges here in this graph. Okay. Another type of question that sort of motivates problems in graph theory would be the following. So you have a salesperson, they must visit a couple of cities, or a certain number of cities for their job. And the question is, can they plan a round trip using highways, enabling them to visit each specified city exactly once? Okay, so in this case, we'll say that the vertices are the cities this time, and we'll say that two vertices are connected if a highway connects the two cities without going through any other cities. And in that case, the question would be, can we find a cycle that contains all graph vertices? And we'll see later in a little while that this is called a Hamiltonian problem. I mean, it's asking whether the graph is Hamiltonian. Another question we might ask about the same type of problem would be, okay, how long will it take, or how many kilometers will it take me to drive through a certain number of cities? So again, here in that case, the vertices will correspond to cities. The cities are connected. We put a value on the edges. In this case, it's going to be the kilometers between the cities. And in that case, we'd ask, and we'll come back to that, what is the minimal spanning tree associated to the graph? Okay, so these are three examples that sort of motivate a little bit of what we're going to look into for the next little while. And more generally, so as what I'll say again, so we'll come back to really a lot of examples of graphs later. But for now, I'm going to sort of look at the mathematics first. But in general, why would you care about graphs? So graphs, as we will see throughout this part of the course, they are useful to encode a variety of relationships. Their graphs allow you to say an object is related to another object. So a person is related to a person, I don't know, a customer is related to a type of product, etc. And these relationships, they are everywhere in the real world. So that means that if you want to encode in your data the relationship between objects that may exist between objects of all types, then thinking in terms of graphs is a very useful way of doing things. And you will see, as I said, many examples of that. Okay. So for now, let's look at the math. Okay, and this is going to keep us busy 2 or 3 lectures, and then we'll move on to examples per se. So first, sort of word of warning, there's several types of graphs, and you will see that essentially the only thing that's going to be constant across everything that we talk about is that every time we'll speak about a set of vertices, okay? And how these vertices are put in abstract, how they are put in relation, is going to determine the type of graph that we have. And so we'll see, for example, an undirected graph, we'll see undirected multigraphs, we'll see directed graphs, we'll see directed multigraphs. And typically, again, I said, like, be careful of the vocabulary in this domain, because oftentimes anything like above we'll call a graph. But oftentimes, also you will see that people use the term graph to talk about unoriented graph. And actually some people talk about graph to talk about what we call an undirected simple graphs. So just be aware of the context. Okay, to begin with, let's spend a little time on what I'll call binary relations. And we saw a little bit of that when we were talking about some notions in algebra earlier, matrix algebra, but let's come back to that. So the first thing is, let's define what a binary relation is. So it's an arbitrary association of elements of one set with elements of another set or the set itself. Okay, most of the time we'll be using relationships between elements of the same set, but this is not an imposed fact. Okay, you can put things between different sets together. And we'll denote typically like this, x or y, to indicate that x and y are related by that binary relation we're talking about. Okay, and I need to find how to change this not here. This is supposed to go through VR, but if two objects are not in relation through that binary relation, we say that they're not in relation. And you will see here that I have invested in high technology, and by that I'm sort of joking, but I'm using one of my tablets to one of my Chromebooks. The reason I pointed out is that it's a little old. Sorry, it's a little old, and so sometimes it'll be a little finicky. But okay, so the typical example that we could think of, one of the simplest ones, would be the relationship between real numbers. If this is the real line that I'm drawing, you can think of element x, element y, and a binary relation between them would be, for instance, that here x is smaller than y. Okay. So that would be a binary relation. And one of the ideas when we're looking at binary relations is to establish what type of properties these relations have. And so this is what we have here. So we'll say that a binary relation is reflexive if for every x in x in a set, x is in relation with itself. It's irreflexive if there does not exist an x that is in relation with itself. It's symmetric if x is in relation with y, means that y is in relation with x. It's asymmetric if x is in relation with y, means that y is not in relation with x. It's antisymmetric if the fact that x and y are in relation with each other both ways means that the two elements are equal. It's transitive if one being smaller than the other means that, and the other being smaller than a third one means that the first, in relation with the first one, and the second being in relation with the third one means that the first is in relation with the third. And finally, the relation is total or complete if there has to be a relation between any elements in the set. Okay? And this will be useful to characterize a variety of things, but in particular, there's quite a few things that we want from relations. And so one that we saw, that's the reason why we talked about this very briefly before, is that one very convenient type of relation is what's called an equivalence relation. So if I have a binary relation that is reflexive, that means x for every element is in relation with itself. It's symmetric. So if an element is relation with R, x and is in relation with R, then y is in relation with x. And transitive, that's what we call an equivalence relation. Okay. A relation that is reflexive, antisymmetric, and transitive is what's called a partial order. Okay. And a total order is one that is a partial order that is furthermore total. Okay. So let me go back to this example. Here you can see that already I have something here. If I want to make this into a partial order, I need less than or equal, because I want that x be in relation with x. So x is less than or equal to x is true. X is less than x is false. Okay, so but if I equip this with a less than or equal to, then I have a partial order, because also you can see that if I add a z here, then x less than y and y less than or equal to z implies that x is less than or equal to z. Okay. And here the order is actually total. Okay, because if I take two real numbers and I try to distinguish them and using this binary relation between them, I can see that any two real numbers on the real line will be ordered that way. Okay. Now, where the problem arises is when you look at 2D space, for instance. So now if I look at the points 1, 0 and 0, 1, then what you can see is that it's going to be difficult to decide on an order between them, because if I look at the first component, this one is bigger than this one, but if I look at the second component, this one is smaller than this one. Okay, so that is one of the issues that we might run into in some more elaborate cases, but here this is not really going to show up, and most of the relations we'll have are actually of the first type that I listed here, the equivalence relations. Okay. Now, let's look at graphs. We're going to start our sort of tour of graphs with undirected graphs, which are the ones that you learn about the most frequently in graph theory courses, the early graph theory courses. So a graph is going to be a set of points and a set of relationships between these points. And the points are what we'll call the vertices, and the relationships are going to be the edges. Now, in later courses, you'll see lectures, you'll see that I'll be talking about directional relationships. And in that case, we'll talk about arcs instead of edges, and we'll talk about directed graphs instead of graphs. But we'll come back to that later. So, to give a precise mathematical definition, an undirected graph is a pair of sets. One of the sets is a set of points, V1 to Vp, and the other set is, okay, so what's this set here? The other set is a set of pairs of points, okay? It's a two-element subsets of this set of points. So the points are what we call the vertices, and the sets of points are the edges or lines in the graph. Okay? And they indicate that a set of points, a set of vertices, a pair, sorry, of points and vertices are in relationship with one another. Now, the order of the graph is the number, the cardinality being the number of elements in a set. So the cardinality of the set of vertices, that's the order. And the size of the graph, on the other hand, is the cardinality of the set of edges. Okay, so the number of relationship between vertices in the graph. Sometimes we'll call P, comma Q graph, a graph of order P and size Q. And also we'll say that a graph is finite if its cardinality, the cardinality of its set of vertices is finite. We say that a vertex is incident with an edge if the vertex belongs to the edge. So remember that the edge takes the form of something like so. So I have a U here and a V there, and that edge I'm going to call UV. I could also call it VU because the order is not important. Okay. So what that means is that the vertex is incident with this edge because the U is in this pair of letters. Okay. Two vertices incident with an edge are its ends. So these are these 2 points here. And an edge itself is incident with its vertices, the vertices that make up its endpoints. Okay, so you can think of things the other way around, where if I have U and V here, that edge is incident to those two vertices because it is they are its endpoints. And we say also that vertices are adjacent if they are connected by an edge. Okay, so the vertices U and V here are adjacent, whereas U and W here are not adjacent because they're not connected by an edge. And if U and V and U and W are distinct edges, okay, so essentially what I wrote here, well, I mean, I should write that way, U and V and U and W, then we say that these two edges are adjacent edges. Okay. A multiple edge is when two vertices are connected by more than a single edge. So if we go back to the problem of the bridges of Königsberg, remember that we had a graph that looked something like so. Well, these edges here are multiple. Okay. A loop is an edge that has the same ends. Okay, remember the ends are the two ends of the edge. So this, for example, if I added this here, that would be a loop. We say that a simple graph is a graph that has no loops or multiple edges. So that graph, the Königsberg graph is not a simple graph, but I could, for instance, make it simple if I just considered this graph here with just these connections. Okay, and a multigraph is a graph that is not simple, essentially. Okay, so the one on the left here is a multigraph, the one on the right is a simple graph. Now, another important relation here is that when you consider a simple graph, it can be defined in terms of a vertex set and a irreflexive and symmetric binary relation over that vertex set. Okay. Remember that symmetry means that if I have an element x and an element y, then x are y implies that y are x, which here means that if I have an edge between the two vertices, I have an edge. And recall that irreflexive means that so the relationship is reflexive if x are x, and it is not, well, it is irreflexive if this is not true. And what we are saying when we mean a simple graph is that there's no loops, so that is excluded here. Okay? Hence the irreflexivity. So x not Rx. Okay. A very important notion, this one, and this is one that we will see both in theoretical graph theory, let's call it, and applied graph theory. Okay, but degree of a vertex is something that is fundamental in studying graphs. So we call degree of an vertex the number of edges that are incident with that vertex. So I'll go back to, let me redraw it. Let me draw the Königsberg bridge graph. The degree here of the different vertices, this here, let's call this 1, 2, 3, 4, the degree of 1 in the graph here is equal to, well, what is it? So there's 3 edges arriving here. The degree of 3 is, there's 4 and 1, 5. The degree of 4, oops, sorry, the degree in G of 4 is equal to 3 as well, and this guy here has degree 3. Okay. And there is this theorem, which is interesting in itself, which tells you that if you have a PQ graph, so a graph with P vertices and Q edges, then the sum of the degrees of all the vertices in the graph is equal to 2 times the number of edges. Okay. I won't go over this. And in general, I would recommend that sometimes you take some of these problems and you play with them a little bit. Draw yourself a few graphs and see that indeed this is what you observe. Okay. And here this would be a case. So here, for instance, let's take this one because we've just written it. So this is a 4. How many edges does it have? 1, 2, 3, 4, 5, 6, 7. So this is a 4, 7 graph. The sum of the degrees is 2 times Q. So this says the sum of 3 plus 5 plus 3 plus 3, which is 14, and it is indeed equal to 2 times Q, Q being 7 here. Okay. So you can play with that from time to time. That's one of the cool things with graphs. The simple cases are easy to write, but they can be very complex. Okay, I don't want to say that everything that we will see here will be easy to show or to give an example of. But okay. So we call odd vertex, any vertex like the ones we have here in this graph, for instance, that is a vertex whose degree is odd. And if a vertex has an even degree, then we say the vertex is even. And there's an interesting result that tells us that every graph contains an even number of odd vertices. And you can see here that this is indeed working out. I've got 4 vertices that are all odd in this particular case. But I could add a vertex here. Oh, I would break it, but let's for the principle of it, break it. So let me make it reddish. So suppose I add 1 here. So what happens here? I have this vertex here now has degree 4. Whoops. Okay, I've added a vertex here. This one has degree 1. So again, I have now 1 vertex with even degree, but I still have 4 vertices with odd degree. Okay. We call regular graph a graph in which all the vertices have the same degree. Okay, and in that case, that degree that all the vertices share is called, well, I mean, it's used to say that the graph is k-regular. Sometimes we don't say that it is k-regular, but let me show you. So, for example, the simplest regular graph would be something like so. Well, I mean, or the simplest regular graph would be one with all the isolated vertices. I do not need to rename my note. So all the isolated vertices, that would be a regular graph. That is a regular graph. A triangle is a regular graph. And then one regular graph that we'll see quite a lot in the future is this graph. Okay, of course I drew this arrow, this edge a little too close. Okay, so here all the vertices have degree n minus 1, okay, 4. Each vertex is connected to 4 other vertices. So this is a 4 regular graph. Okay, and we'll see this graph over and over again in this course. Now, isomorphic graphs are graphs that share the same shape. Okay, isomorphic means the same shape. And so here, what this says is that I have 2 graphs, which if I essentially make them so change the names of the vertices, I have a similar graphs. So let me just point out what this looks like. I could have a very simple case. I could have a graph xy here. I could have another graph u, v here. Well, if I make a function that transforms x into u and y into v, then I see that this graph, these 2 graphs are the same. Okay, I just change the labels on the vertices and I have 2 times the same graph. Okay, and this is very useful. Now, it turns out that isomorphisms go both ways. Okay, that's one of their definitions, is they are functions, they are mappings that sort of map all points into another set of points, but that mapping can be taken back. So that means that if I can change my vertices, as I was explaining here, I can change them back into the original vertices. And that means that if a graph is isomorphic to another, then that other graph is isomorphic to the first one. Okay, and that means that what we have is an equivalence relation. And yet again, an equivalence relation, and this is not the last one we'll see. So the relation graph is isomorphic to of a graph is an equivalence relation on the set of all graphs. So that means that all the graphs that are isomorphic to each other, they can be represented by a single graph in that category of that class of graph that share the same properties. And that means in particular that they share all the same properties in terms of, for instance, degrees, but a variety of other things as well. Okay. What happened here? Yes. Okay. Now, another thing that I'm going to do with graphs is consider subsets of them. So I need to relight my tablet. I've switched. There was a mishap when I was filming this, and I've switched from using my Chromebook to using a tablet, which hopefully works a bit better than my very old Chromebook. So a subgraph is a graph that is composed of a subset of the vertices and the edges of the original graph. Okay, there's no prescription on what set of vertices and edges you take. You just take a subset of them. And so, for instance, there's going to be a bunch of different graphs that I can consider. So let me again, we'll always be playing with very simple graphs. But okay, this is a graph with 3 vertices, and you could think of making a subgraph that would look like so, or you could look at a subgraph that would look like so, or whatever else. Okay, so you can take a subset of the vertices, a subset of the edges, and that is the graph that you're looking at. When we have 2 graphs, we can put them together. Putting 2 graphs together means putting together their vertex sets and their edge sets. The intersection of 2 graphs, on the other hand, is the graph that you get by considering the intersection of the vertex sets and the intersection of the edge sets. We say that 2 graphs are disjoint if both the intersection, when you take the intersection of the 2 graphs, you end up with an empty set of vertices and an empty set of edges. Okay, and in that case, we'll just denote the empty set altogether to say this is the empty graph. And in that case, if the intersection of the 2 graphs is empty, then the graphs are disjoint. The complement of a graph is, that's an interesting one. You take, that complement is based on an edge set. Okay, so you take a vertex, so you have a vertex set, and you take an edge set that is the edges that are not present in the original graph. So now let's look at one of the most important properties of graph, and that is connectedness. So connectedness is another one of those properties that you're going to see both in theoretical work about graphs and in their practical uses, because this is a measure, an evaluation of how objects are in relation, whether long or short or long-term, long-distance relation between each other. Okay, so I need to be very careful because I've paused this recording many times. So 2 vertices are connected if either they're the same or there exists a path that links them. And we'll come back to paths in a second. But for now, let me show you this without getting into details, the definition being given later. So if I have a vertex, what this is saying is that there is a way of going from vertex U to vertex V. So either they're the same or there is a set of vertices and edges that I can follow between one and the other. Okay, and remember that it doesn't matter what direction I take that. And so if a graph is such that every two vertices in the graph are connected, then we say that the graph is connected. Otherwise, we say it's disconnected. Okay, so a graph like I've just drawn is a connected graph. A graph that would be something like so. Okay, I'll highlight that it's those four vertices. That graph is disconnected because if I'm here, then I cannot go to the either any of the other three vertices, and if I'm in one of those three vertices, I can go to the other two, but I cannot go to that isolated vertex here. Okay, so this is a disconnected graph. The one above is connected. One remark is that a connected graph on p vertices, so a graph of order p, has to have size at least p minus 1. And this is very simple to see from that first case I was making. That would be the simplest case. Suppose I have a bunch of vertices that are arranged like so. How can I make sure that each of those vertices has access to every other vertex? Well, the simplest way is to connect them like so. I should connect here, okay? But if I do that, you see that here I had 5 vertices, I had to draw 4 edges. And this is the minimal connected graph. And so that's what you have here, okay? Now, this connectivity is an equivalence relation. Okay, so if we denote that triple equal the relation x is y or x is not y, and there is a path connecting x to y in the graph, so that means x and y are connected. This is how we defined connectedness. Then we see that we can check that those three properties hold. X in relation with x, okay, because y with x here because they're the same. X equals y in that sense means that y equals x, because if there's a path between x and y, there's a path between y and x. And the fact that there's a path between x and y and a path between the y and z means that there has to be a path from x to z. Okay. And this allows us to look at graphs that are not connected, and that's going to be more frequently the case than connected graphs. Well, it depends what we are working on, but when we're looking at data, it will be more frequent that the graphs are disconnected rather than connected. But if they are disconnected, then we will look at what is defined here, the connected components. Okay, so the connected components of a graph, and let me draw an example graph. So my usual suspects, a triangle, and that. So this is the graph that I'm considering. So you can see that this graph is not connected. Okay, but if I look at subsets of vertices on which I can define this equivalence relation, I can see that what's going to happen is that those three vertices, they belong to the same component. They indeed are connected to each other. These two vertices are the same. I mean, they are also connected to each other. They're not connected to the remaining others. And that one is true as well, because remember that we said x equals x, x equals y, x equals x. Okay, so so that one is also a connected component. So this graph is disconnected, and it has three connected components. And often we'll just say components. Okay. Now, one of the things we often look at is way to get this connectedness to deteriorate. And so, because it's some vertices are going to, if you think about a graph as showing all the relationship between objects, the vertices or the edges that sort of make the graph lose its connectedness, they play a special role. I mean, they're going to induce. So suppose you have a graph that's completely connected, and then when you delete a vertex, then the graph becomes two components instead of one. Then that vertex is important in a way. It's It's organizing the graph in a sense. Okay, so we call vertex deletion the process through which you remove a vertex. So this is quite simple. If I am to remove, if I am to remove vertices, let's say I remove that guy. Then what I do is I also remove the connected, the incident edges. Okay, so the graph that remains after deleting that vertex on the top right is the one that I've just circled. Is it, the second definition here, is it a cut vertex? Well, I have a connected graph to start with. I've cut that vertex there. The graph that I get is still connected. So this is not a cut vertex. Okay, that subgraph that I have now, that I've obtained, is still a connected graph. On the other hand, if I look at a graph like this, and I delete this vertex, then the remaining graph is just a graph that has these two isolated vertices. It is disconnected, therefore that vertex in the middle is a cut vertex. And you see what I meant when I said that vertex encodes a relationship that is fundamental to the graph. And you could imagine that there would be a whole lot of vertices here and a lot of vertices here, but the relationship between all these lots of vertices might have been lost by just severing that vertex in the middle. And we have the same notion in terms of edges. Okay, so edge deletion is this time you delete edges, but you do not remove the adjacent vertices. Okay, and we call bridge an edge which is such that if you remove it, then you get a disconnected graph. Okay, so this is the same. Let me draw the same cases as before. Suppose I remove, say, this edge and this edge. You can see that the graph on the left is still a connected graph. Okay, I can still go from any vertex into any other vertex. It just takes me longer to go from that guy to that guy, but but I can still do it. Okay, so this is not a bridge. On the other hand, on the right, the graph that I get is a disconnected graph, and therefore this is a bridge. Okay, there's this theorem that tells you that if you have an edge, it is a bridge if and only if it doesn't lie on any cycle of G. And we'll come back to cycles later. I'll just leave that here, but once you've looked at this, maybe when you're playing around, you can look at this result. Okay, another very important property of graphs that we are interested in are walks, trails, paths, and the like. So let's start with a few definitions. So first of all, a walk, and I've talked about walks already. Well, I've talked about paths, but you'll see. So first of all, a walk is a non-empty alternating sequence of vertices and edges. Okay, so you go along, you start at a vertex, you go along an edge, follow another, get to another vertex, follow another edge, or maybe the same. It doesn't. There's nothing precluding you from taking the same edge twice. Okay, and that is what we call a walk. So if I'm looking at examples, well, I could, if this is U, E, V, sorry, I'm going back to black, U, E, V, E, U, for example, would be a walk. So would be E, U, E, V, V, E, U, etc. The length of a walk is how many edges you go over during that walk. Okay, so if that's it. So if you think about this walk here, for instance, it has length 4. The walk is closed if you end up where you started. Okay, if the initial point is the initial vertex equals the terminal vertex, then the walk is closed. A trail is a walk along which all the edges are distinct. So if I look at these walks that I've highlighted here, the first one is not a trail. The second and third are trails. Okay. And a path is one where all the vertices are distinct. Okay, so trail is all the edges are distinct. Path is all the vertices are distinct. And if you look at the vertices and edges determined by a trail, that is a subgraph of the original graph. A very important notion, both in applied and theoretic graph theory, again, is the distance between two vertices. So it will happen very, very often that there are many different ways. So let's call this U and V. There might be very many different ways to get from one place to another, one vertex to another. The distance between two vertices is the minimum of the paths, of the path lengths from one vertex to another. Okay, so here that would be 1, because I can go from U directly to V here. And if there's no connection, if I have a graph like so, then we denote, whoops, it's an ugly infinity, we denote this to be infinite. A circuit is a trail that has at least 3 edges and that finishes where it started. Okay, and that's why you need 3 edges, because otherwise, let's see, this is, I'm not going to get a circuit here. I need a third one if I'm going to end up where I started. A cycle is a circuit that does not repeat any vertices. Okay. And the length of a cycle is how many edges there are on this. And so if you remember, we saw some results before about cycles and etc. And this is where this is coming in. Then we call Eulerian trail in a multi-digraph. So this is important. Multi here is an important characteristic because we do want to think about the bridges of Königsberg. An Eulerian trail is one walk, that uses only each edge only once. And this is exactly what we want in the bridges of Königsberg problem. If there is an Eulerian trail in the graph that you're considering, then you say that the graph is traversable. If you can go through all the vertices and edge, so if you can have all the vertices and all the edges, then you have an Eulerian circuit. Okay, if there is an Eulerian circuit, then you're talking about an Eulerian graph and an Eulerian multigraph, depending on the case. Okay, so if that's a circuit, so you have to finish where you started. So you have to go through all the vertices, all the edges, and start back where you came from. So, bridges of Königsberg. Let me go back to a case where I can show. So a question here in terms of what we just defined is this multigraph traversable? That was Euler's initial question. Okay, so is it possible to go through each edge in this graph once, only once? And is it Eulerian or altogether? So is it possible to do that starting in one place and coming back to the same place? Well, there's a bunch of theorems that we can use to help us answer this question. The first one is here. A multigraph is traversable, so there's an Eulerian trail in it, if and only if it's connected and it has exactly two odd vertices. And if that is the case, if there is an Eulerian trail, so then that trail has to start at one of the odd vertices and end at the other odd vertex. Okay. And the question of whether the graph is Eulerian is answered here. A multigraph is Eulerian if it is connected and every vertex of M is even. So let us go back to our favorite graph. And let me indicate the degrees. This is 3, 3, 3 and 5. So first question, that way, is it traversable? Does there exist an Eulerian trail? So M is connected, yes, and it has exactly two odd vertices. Definitely not. They're all there's four of them. It doesn't have two, it has four. So that is not good. It doesn't work. And is it Eulerian? So can we have a circuit in there? Well, even less so. Okay, it's connected and every vertex of M is even. Definitely not. All of them are odd. So that is not working either. As an exercise, you might want to play with this and imagine this problem and see how you can modify it to see, with the same number of islands, if you were building bridges to satisfy Euler's desire to visit every bridge without ever crossing again, where do you need to add bridges to this graph to make it have an Eulerian path? Okay, you can play with that a little bit. Remember, you're not allowed self-loops. You can't put a bridge that just goes up in the air and takes you back to where you were. You have to cross the rivers. Okay. If it is, if you know that there are only two odd vertices, exactly two odd vertices, then you can use the algorithm that's highlighted here, and I'm not going to detail it, but you can use this algorithm, and this algorithm will produce a trail that is going through all the edges. And if you have a circuit, so if there's a connected graph that has no odd vertices, then you can use that algorithm to find a circuit. Okay, and I recommend that you play with it with simple graphs to see if you can get it to work. Now we have similar notions for paths with the vertices. Okay, so we were talking about edges before. Let's look at vertices. So if a path contains all the vertices in the graph, we say it's a Hamiltonian path. If a graph has a Hamiltonian path, we say it's a traceable graph. If a cycle has all the vertices in the graph, it's Hamiltonian cycle. And if it is a Hamiltonian graph, if there's a Hamiltonian cycle, then it is a Hamiltonian graph. And I'm not going to go into this. It's another interesting problem, but here are a few theorems that tell you under what conditions you might expect to find a graph that is Hamiltonian. And I'll point out that oftentimes you use that to say that a graph is non-Hamiltonian also. Okay, so because you can see that first result, if you have a graph of order greater than or equal to 3, and its degree of every vertex is at least greater than or equal to half of the degree of half of the order, then the graph is Hamiltonian. So, for instance, if you have a graph and you have a vertex of degree that is larger than so p is larger than or equal to 3. If you have a vertex of degree 1, then it's not going to be Hamiltonian, for instance. Okay. Now let's look at a few interesting graphs that we will see quite a few times and that allow to think about things. The first type of graph we've talked about already, in a sense. I mean, I've shown you an example, but without pointing out that it was this. We call a graph complete if every two of its vertices are adjacent. And I drew a complete graph earlier, but I'm going to draw again. I pointed out that it's a graph that we will see quite often. And this graph here is such that every vertex is adjacent to every other vertex. Okay, and it satisfies the following definition. Simple. It is simple. Okay, there's no loop. There's no multiple edges. A simple graph that is complete on n vertices is called an n-clique. It is typically denoted k sub n. So this is k5. Okay. A bipartite graph is a graph where if you put the vertices in two sets, then all the vertices in one set are not adjacent to any of the other vertices in that set. They can only be adjacent to vertices in the other set. Okay, so I would have a set of, so typical example would be something like this. I have a set x1 of vertices, a set of x2 of vertices. Vertices here are adjacent to some of the vertices in the other place, but there is no such connection as that one. Okay, that doesn't exist. So that's a bipartite graph, and this is another type of very well-known graph, and I'll actually draw one of the most interesting ones, which is this graph here. So this is a graph, I'm going to make it bipartite. Okay, so the graph is this whole thing. And so, this is not connecting well. Okay, so here every vertex in this, let's say x1 here and x2, every vertex in x1 is connected to every vertex in x2, and vice versa. So this is a complete bipartite graph, and this one would be denoted K33. It indicates the number of vertices in both subsets of vertices. These two are very important. We'll come back to them later. K5 and K33. A tree is any connected graph, so it has to be connected, that has no cycle. So typically we call them trees because we'll make them look something like so. Okay. We'll come back to trees later. A cycle is a connected graph of order n that is a cycle on n vertices. So that means a cycle looks something like this. Square is a cycle of C4. Okay. And the more vertices you have, but it's still going to be connected only to the neighbors. A path is what we've been drawing quite a few times now. Okay, path is something like so. Okay, it's a connected graph that has n greater than 2 vertices and n minus 1 edges. Two of the vertices have degree 1, the endpoints, and the other vertices have all degree 2. Okay, and finally, the star is another type of graph that is important, and this would be S5. Okay. This is a star. The central vertex is connected to n minus 1. So here, n minus 1. Six. So how many? I can't count. There are 6 vertices here. So the center is connected to 5 other vertices, and each of the peripheral vertices is connected only to the center. Okay. And the last thing we'll talk about is planar graphs. So a planar graph is a graph that can be drawn in the plane with no crossing edges. Okay. Except perhaps at the vertices, if you count that something like so is an intersection, for example. Okay, but except at the vertices, the edges do not cross when you draw them. So, for example, when I draw this here, the vertices are crossing, but this. Okay, so this is a planar graph that I've just drawn, because you can see what would happen if I moved this vertex here to here. I would have this, or how would I do this? Yes, if I would have this, that. So if this is 1, 2, 3, 4, so this is 3 and 4, I'm not moving. I have 1 is here now, and 2, oops, what is happening here? 2 has moved here, okay? And so what I have is 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, and 4 is connected to 1. So this is a planar graph. Okay, now it's plane. Okay, just so you see the difference, I've linked things here, so you can see this. Maybe I'll make it bigger. Bigger me doesn't help. Bigger this. This is a game. I don't know if you've ever played it. Take it. Smallest one is probably easiest to deal with here. The idea is that you need to move the vertices in such a way that the graph becomes planar. Okay, so plane. Okay, so the graph is planar by assumption, and the idea, this is a way to lose a lot of time. Got it. Okay, you can make it a lot of points, but I'll point out that it knows how to solve itself. But this is the difference. Okay, this, if I take that guy, this is a planar graph, because I know, because of the rules of the game, that it is possible to write it as a plane, or to make it appear as a plane graph. No, that is not what I wanted to do. This is what I wanted to do. Okay. So let's not worry about this one. Okay, this is something you might want to look into. Plane graphs have interesting properties, but let's not worry about this right now. There's let me zap this. This is an important one. Remember, we talked a bit about K33 and K5. I pointed out that they are very important graphs, and one of the reasons is because of this theorem. A graph is planar if and only if it does not contain a subgraph that is isomorphic, so of the same form as K5 or K33, or any subdivision of K5 or K33. Okay. So if you're looking to see whether a graph is planar, and you find something like this, you find something like resembling K33 or K5, then you know that your graph is not planar. Okay, this is how this result is used most of the time. And this brings us to a very interesting quite theoretic problem, but that has applications in real life that I'll show you in a moment. And that is what's called the coloring of a graph. So we call coloring of a graph an assignment of color to the vertices. So that adjacent vertices, so vertices connected by an edge, have different colors. And we call n coloring a graph, the act of coloring a graph using n colors. And we say that a graph is n colorable if we can find a coloring with n colors of that graph. Okay, so I'm going to be using colors a little bit here. Let me look at colors here. You can see, okay, I'm going to start painting vertices. I need to paint the vertex into a color. It's an adjacent vertex, okay, so I can't have the same color. That's the coloring problem. So here I've colored my graph. This is a free coloring of the graph, and the graph is colorable. Okay. And we call chromatic number the minimal value of n for which an n coloring of the graph exists. Okay. So that's a very important number in graph theory. There's a lot of people that spend a lot of time looking at properties of colorings and the chromatic number of graphs and so on. And this is also something that has applications in real life. I'll show you in a moment. So some properties of the chromatic number. The first one is quite easy to see when you think about it. Coloring the chromatic number of a graph with no edges is 1. Well, okay, I can take a graph like this, and okay, I'm not going to paint it in another color. Let's just paint it black and just say, well, these three vertices, sorry, they're not adjacent, so I can use the same color for all of them. There's not a problem. These are a few results. The one I want to draw your attention is the last two. So for any graph, the chromatic number is less than or equal to 1 plus the maximum degree of the graph. Okay. So that's an interesting property. Okay. If you think of any graph that you have, the highest degree in all your vertices in the graph is going to determine how many colors, like an upper bound of the number of colors that you need to paint your graph, to color your graph in such a way that no two vertices, adjacent vertices, have the same color. And that last one is if you have a planar graph, then the chromatic number is less than or equal to 4. Okay, and that brings us to a real life problem. That will be essentially the end of this lecture. So this is where the coloring problem comes, well, where it can come. How can you color this map in such a way that all states that are adjacent have different colors? Okay. And so you can see here, this map here has been colored in such a way that no two adjacent states, if they share a boundary, have the same color. And that is a remark that I'll make. Okay, so in terms of a mathematical representation, if what we are going to do is what we did with the bridges of Königsberg. So I didn't do that in this graph. I didn't plot it here, but you would put a vertex in each state here, and you would draw an edge if the states share a border. There is one little quirk that I'll highlight here, or actually I'll make myself big this way I can highlight. So typically when we do this, we consider that this is not a common border between the 4 states. So Arizona here and Colorado do not share a border. And likewise, New Mexico and Utah do not share a border here. Okay, So, but it still poses problems because they're quite close together, but they shouldn't be considered like sharing a border, those across the diagonal from the borders. Okay, so the mathematical representation of the problem is I have my vertices corresponding to the states. The vertices are adjacent if the two states are adjacent, and then the question is, what is the chromatic number of a graph associated to the map? Okay, and it's called the four coloring theorem. It was an enormous endeavor for many, many years. It was proved a few years back now, but I mean, compared to the history of mathematics and how simple that question may sound, it wasn't proved that long ago. Also, I mean, I don't remember exactly when it's considered proved for sure, but it's less than 50 years, I believe. So this is not something that was easy at all. Whereas, I mean, when you look at this, you think, oh, okay, it's easy. So this is called the four-color theorem, and it tells you that any map, any planar graph, has a chromatic number that's less than or equal to 4. So the maximum that you need to be able to show this is 4 colors. And that's it for... Oh, no, not... Haha, I thought one last little thing. This is an algorithm, and I'm not going to show you the idea, but I mean, very briefly, this is how you would color a map. And you can play with that. Again, it's another one that you can play with. And I'll just point out that I didn't take Canada because the coloring of Canada is too easy, especially in the West, because you just need 2 colors if you don't count the territories. If you count the territories, it becomes a bit harder.